Hello everyone! Our goal today is to use integration by parts to evaluate the asymptotic behavior of this integral as x goes to infinity. Let's see. The integral we are tackling is from 0 to x dt, t minus 1f exponential minus t, and we can rewrite this as two parts. First, from 0 to plus infinity dt, again t minus 1f exponential minus t, minus the integral from x to plus infinity dt t minus 1f exponential minus t. The first integral is already known to us. It's the gamma function at 1f, which is exactly square root of pi. Using integration by parts on this thing, we get minus integral from x to plus infinity, and then we move the derivative onto these square roots, and that gives us minus 1f t minus 3f's exponential minus t divided by minus 1, plus some boundary term from x to plus infinity of t minus 1f exponential minus t divided by minus 1. Let's now simplify these two results. We get 1f integral from x to plus infinity dt t minus 3f's exponential minus t plus a boundary term which is given by, well, when this thing is evaluated at infinity, it gives us 0, and then subtract this thing evaluated at x, but because we have a minus sign here, we get a plus. So we get 1 over the square root of x exponential minus x. Because we are going to use integration by parts systematically, we should check the calculations each time we do it. So looking at it again, we notice that we missed a minus sign here. I hope you have caught it. And on this side, everything is okay. Let's now move further and use integration by parts again, this time on this thing. This integral here, let's call it 2 stars, and 2 stars is the same thing. Well, using integration by parts, it gives us a minus sign, minus 1f, integral from x to plus infinity dt, and now again we move the derivative from this side to this side, so we get minus 3f's t minus 5f's, and here minus exponential minus t divided by minus 1, on which we add the boundary term from x to plus infinity of what? Of this thing here. So we get minus 1f, 3 minus 3f's exponential minus t divided by minus 1. Simplifying now our result, we start by lumping all constants and signs on this side, so we get minus minus plus, minus minus plus, and then the constants 1f and 3f's. So we get 3, 2 squared, and then the remaining part of the integral, dt, t minus 5f's exponential. Now the boundary term, we again lump our constants and signs, so we get plus 1f, and this thing evaluated at infinity and then at x. At infinity it gives us 0, and so we get minus 1 over x 3f's exponential minus x. We can simplify further our boundary term by making it look like the boundary term on the previous integration by parts. As a result, we get minus 1f 1 over square root of x times 1 over x exponential minus x. Joining now our results, we get the following thing. Looking more closely at our formulas, we notice that this thing here also shows up here. And so let's factor this term. We get the following final result. Square root of pi minus exponential minus x, square root of x, and then 1 minus 1f times x plus the integral here. So the integral goes here. We have just found 3 terms in our expansion here. We can now go further and now repeat integration by parts to get more terms. But for this lecture, I will just finish here and leave it the work to you. However, I'm going now to evaluate the size of this integral, meaning the size of our error if you decide to truncate this part. To create an upper bound for this integral, notice that we eventually want to take x to plus infinity, so there is no problem in assuming right now that x is larger than 1. In that case, this t here is smaller than 1 because it decays as t gets larger, and thus we can replace this thing by the largest possible value in the domain of integration, which occurs when t is exactly equal to x. And so the integral here, 3 stars, so 3 stars, is smaller than 3 divided by 2 f's, x minus 5f's, and then the integral for x to plus infinity of this exponential is essentially e to the x. Rewriting now our upper bound, we get that this thing is 3 divided by 2 squared, 1 over square root of x, 1 over x squared, and then times this thing, e to the minus x. This is supposed to be minus, okay? What this means is that the integral that we are considering here can be said to be of the order, so it's a big O, of this thing here, 1 square root of x, 1 over x squared, exponential minus x. In the regime when x is very large, so we must add when x goes to plus infinity. And finally, we can write our expansion that we found so far. We have our original integral here, and we also have the 3 terms here that we just found. Let me paste it here. On top of those 3 terms, now we add the term of order given by this. All this formula now is valid on the regime when x goes to plus infinity. And finally, comparing this term of this order with this term here, we notice that this thing here is negligible, and so we can just forget about it and say that this integral here is what we call asymptotic to this thing in the regime where x goes to plus infinity. To check our expansion that we got so far, let's make a graph of this integral as a function of x and also of these terms. What we get is the following graph. In blue we find the integral, and in yellow the 3-term expansion. And you can see just for x larger than 4 that the 2 results are almost glued to each other, which confirms that we have a good expansion. See you next time.